So now we will look at the electric field. So far we saw the electric force, and now we will look at the electric field. So this is something like a gravitational field. For example, this is the Earth, and you have a mass over here. Some mass m is pulled this way, and the force of gravity is g, mass of the Earth, times this little mass over r square, where r is the distance from the center of the Earth up to here. That's the distance r, and it's pointed in this direction. So that would be, let's say, the unit vector r pointing this way. Now, similar to this, if we have an electric charge, let's say that's a positive charge, and we have another small positive charge here, then it's going to be pushed away with a force given by K. This is capital Q, that's little q, so Q over r square. This distance is r, and the unit vector, well, in this case, is pointing away from it because both of these are positive. So if we rewrite this as mg, we'll just look at the magnitudes for a minute, and we write that as a force, that's mg, and if we cancel out the masses, then the g is g, mass of the Earth, over r square. So that's the acceleration due to gravity at that point. Now, whether or not you have a mass will not affect the value of g. So if you have a bigger mass, or you have a tiny mass, or you don't have any mass, the value of g at that location will always be the same. And then the force on any mass that comes in there is simply going to be the g times that mass. So similarly, we can say that the force electric is, well, this would be the force gravitational, is going to be K Q over r square and another q, and we can write that as an E times q. So the E corresponds to the g, and we can cancel out the q's, and therefore the E is K Q over r square. And then any force, if you bring a charge, so if there's no charge particle here, we still have the electric field. Just as if there's no mass here, we still have a gravitational field. So the electric field does not depend on the second charge, it only depends on the first charge. So the point here, which is at the same distance, all points along the same distance would have the same electric field. Well, the directions would be different, but the magnitudes are the same. So an electric field is a region of space surrounding the charge where the effect of this charge is felt if we bring a second charge over here. If we don't have this second charge, the electric field is still there, but there's nobody to experience it. But if you bring a charge, then it will experience that field. Now, because this force is a vector, the electric field is also a vector, and the direction of E is the same as the direction of the force. So in this case, the force is outwards, so the electric field is also pointing outwards. So if we now draw an electric field, let's suppose we have a charge, positive charge. So over here, the electric field is going to be pointing away from it like that, and over here it's going to be pointing away, so the electric field is going to point away from it in all directions. And if you get further away, so r gets bigger, E gets smaller, we can say that as we get further away, the electric field gets smaller and smaller and smaller. So it keeps getting weaker as we go further away in all possible directions. Now, if this charge were negative, and if we bring a small charge over here, and this charge is again plus Q. Okay, the test charge is a positive charge. Then the force of attraction is inwards, and therefore, therefore the electric field is also inwards. And so for a negative charge, the electric field would point towards the center of the charge from all directions. So for a positive charge, the electric field points outwards. For a negative charge, it points inwards. The units of the electric field, well, it would be, this is the units of the force is newtons, so its electric field is going to be F over Q, so it's going to be newtons per coulomb. So that's the unit for the electric field. Now, we can say that if this is a stronger charge, well, the electric field will be stronger. We can show that with a longer arrow, or we can also show it with more lines. So one of the ways of showing this is that if you have a small charge, you have a few lines. If you have a bigger charge, you have many, many lines going out. And then let's say that we have a line that's going along this direction, a line going this way. So these become what we call the electric field lines. Now if I have a charge here and I have an electric field lines going outwards from it, then in this part the electric field line density is smaller, here it's bigger. So if I have a unit area here, I have two lines passing through here, same area here would have one line, so the field gets weaker. So in a way, more lines closer together imply a stronger field. Now if we have two charges, so let's suppose we have a positive charge and its lines of force or the electric field lines are going outwards. Okay, they're all pointing outwards. And we have another positive charge, its field lines are also pointing outwards. So what happens here or here? We have, if you put a point charge here, it's going to be pushed this way. If you put it here, it's going to be pushed this way, or sorry, this way. But what if you put it here? It could be pushed this way or this way, and we should have no ambiguity. Or you can also say that, well, the two will add up to give us a resultant in this direction. And so we can't have these two lines here. We must have only one line pointing in this direction. So what happens is that these two lines sort of push each other and go like this. And similarly, when this is bent, this one will also bend away from it. And so will all of these. They will all bend away from each other. And the result is that we would get something like this. If these are two positive charges, then electric field lines would go like this, and these are pointing, if they are both positive charges, they're pointing like that. So they will get closer and closer, but they will not intersect. So electric field lines cannot intersect. Now if one were positive and one were negative, then lines are going out from here and they're going in here. So a line that's going out here, going in here, it would pull it in and goes like this. And this one would go all the way around and come over here. And if these are the only two charges in the universe, well, every line coming out from here would ultimately go around and come in here. And same on the lower side. So you can see nicer pictures of this in the textbook. Now, just as we had, well, let's look at if we have a parallel plate. So we have a plate here and another plate here, and we make this plate positive and this negative. What's the electric field between them? So seen from the side, we have these two plates. this plate is positive, this is negative. So electric field lines will go out from here and they're going to go in here, so they will just go straight into these if this is like large compared to the distance. But near the edge it's going to be like this, so it's sort of curved, and lines going out from here would ultimately go back in here, and similarly all around. So in this part we have what we call a uniform electric field. Uniform meaning that the lines are parallel, the electric field strength is the same everywhere inside here.